Okay, good afternoon, students. This is the final lecture of Chapter 4. To be precise, it's Lecture 8 of Chapter 4. And I want to wrap up a small discussion on the concept of a supersonic diffuser idea. I think we have covered pretty much everything else in this chapter. I just wanted to devote a few minutes to the concept of a supersonic diffuser, and I don't anticipate this lecture to be pretty long-winded, so we should probably get done in about 20 minutes or so, hopefully. And in the last lecture, towards the end of last lecture, the last few minutes, I introduced the concept of a supersonic diffuser. A supersonic diffuser, particularly a converging diverging supersonic diffuser. There are other kinds, okay? So we're going to talk about this converging diverging supersonic diffuser. Shows up in the context of what is called as air breathing propulsion. So as you know, in air breathing propulsion, what you need is a fuel and an oxidizer to interact. And in the case of air breathing engines, the fuel is some kind of flight fuel, and the oxidizer in this case happens to be air. So the air kind of comes in and then it mixes with the fuel, it combusts. So why do you need it to combust? Because combustion increases the stagnation temperature, and as it increases the stagnation temperature, if you combust in a fluid that is practically stationary, then any increase in temperature is going to increase the stagnation temperature, right? And if it increases the stagnation temperature, if you assume it's an ideal gas equation of state, then if you're going to assume it follows an ideal gas equation of state, then your P naught is going to increase, and higher P naught compared to the same back pressure value across a converging diverging nozzle means higher Mach numbers at the exit plane, which means if you have higher Mach numbers at the exit plane, you generate more momentum and hence more thrust. And the whole idea of this propulsion mechanism is to generate thrust. So the essential issue in air breathing propulsion is this, right? So you're taking in air from the outside, and this flight is already operating at supersonic speeds, say, okay? So then what is happening is it is taking in air that is at supersonic speeds. And for combustion to happen, so which means for combustion process to be efficient, so let me write it, let me underline these lines. So for efficient combustion, this fuel and this air need to mix efficiently, which means the flow needs to slow down. Only then they can efficiently mix with each other. And obviously, once they the air slows down, can mix with the fuel, undergo combustion, which increases T naught, which in turn increases P naught. This P naught accelerates the gas through the converging diverging nozzle, and thus converting what is called a stagnation property, a large stagnation property isentropically into a larger amount of kinetic energy because of the nozzle. So that's what we learned, right? The Mach number is essentially the relative proportion of kinetic energy to internal energy. So this gas that just underwent combustion will have a lot of internal energy, and now you push it through a converging diverging nozzle, it's going to convert a lot of that internal energy into kinetic energy, and hence a lot of momentum and hence thrust. So that is the essential idea of a converging diverging nozzle based thrust generation system, and generic idea for any such propulsion systems. So the inflow is supersonic, so you need to slow down the flow. And what are the mechanisms that you can slow down the flow? You can just block it, right? I mean, you can just block the flow. And as you block the flow, it's not, or you can constrict the flow. And it's not going to be that easy because it's at supersonic speeds, so it won't sense the constriction. So the only response this flow is going to have is to undergo a shock and convert the flow into a subsonic flow behind the shock, which in turn is going to sense this constriction and try to slow down. The problem with this approach is you want your combustion process and the energy addition process to be efficient, right? So now you have this inflow that just underwent a shock to slow down, which means you're losing a lot of the P naught or the stagnation pressure associated with the inflow. Now you lose a lot of this P naught, then you take this residual flow with reduced P naught, then you need to add that much more fuel and burn that much more fuel to increase the P naught to the value that it originally had in the, from the to the value of the incoming flow. Okay, and then on top of that, you need to burn more fuel to increase the P naught further, so that you can generate increased momentum and hence increase thrust. So the basic idea here is, how can we slow down the flow efficiently without losing any of the P naught that is inherent in the flow that is obtained, that is generated because the flight is already operating at supersonic speeds, right? So you don't want to lose all that incoming momentum. You don't want to kill all that incoming momentum in the air. You want to store it as internal energy, and the way to store it is to isentropically slow it down into a stagnation state. And how do we isentropically slow down the fluid? The way to do that is to use a converging diverging nozzle in reverse. So which means now you have supersonic inflow and you have a converging section. So the supersonic inflow is going to slow down through that converging section, and if it is operating at what is called as a design condition, then you could in principle choke it at the throat, and then the diverging section, the flow can either accelerate or decelerate, right? And most probably in this case, it is going to decelerate further into subsonic flow, simply because the back pressure in the combustor is going to be high enough to warrant a subsonic flow. So when that happens, then the flow is going to slow down isentropically into a subsonic flow, and at that point you can have a very efficient way of mixing the fuel and the oxidizer so as to have a very efficient combustion process. The problem is the following, okay? So if you're using a nozzle like this, then there is a design Mach number, MD, that is associated with the nozzle, right? And if the nozzle has a shape, so if this AI is the area of the inlet and AT is the throat area, then this AI by AT is going to give you the nozzle shape, and there's a characteristic supersonic Mach number that is associated for this nozzle, associated with this nozzle design, that you can get from your isentropic flow tables. So for isentropic behavior, this AI by AT will give you a design Mach number. So in other words, in any of your problems, your MD, your design Mach number, and the area ratio, that is AI by AT, are equivalent pieces of information. And so only if the flight is traveling at this design Mach number would this nozzle work, because then it would isentropically, then it's operating at the design Mach number, which means this nozzle designed for this Mach number can isentropically slow down this fluid. However, it is not possible to operate under design conditions all the time. For example, one of the most prevalent of design conditions is what occurs when you typically start up the flight, or when you're trying to slow down from your cruise speed, okay? So either you're accelerating towards your cruise speed or slowing down towards your cruise speed, right? So what happens? And it is at these times that the combustion process becomes very inefficient. And in this day and age, when you have so much effort to make this reduce the carbon emissions and all that, then this becomes a key issue, okay? So let's look at the situation when you're operating in an off-design condition during the startup phase, which means let the flight be cruising or trying to operate at a Mach number MI, which is smaller than the design Mach number, right? Okay, so the design Mach number can be viewed as the cruise speed. So and this MI is something smaller than the cruise speed, but this MI is supersonic, so it's greater than 1. What happens if it's subsonic? Then subsonic is not a problem, because subsonic can sense this slowing down of the can sense this obstruction from the combustor, and it can slow down accordingly and isentropically. The problem with this is always with the supersonic flows, because a supersonic flow, if it senses an obstruction, one, it cannot sense an obstruction, and if there's an obstruction, then the only way it will slow down is through a shock. And the shock is a non-isentropic process, and that is where the issue is. So if MI, so MI less than 1 is a trivial case, okay? So let's consider MI greater than 1. That is, the flow is supersonic, but it's not yet operating at cruise speed. Then Then for the design, if MD is the design Mach number for this diffuser, then we have, under isentropic conditions, you can identify what is this AI by A star and AI by AT, right? So this AI by AT is the guy that corresponds to MD, right? But now you're operating at MI, which is smaller than MD, which means now the corresponding area ratio for MI is going to be AI by A star, okay? So let me write it this way. So let's remember this plot, okay? This is a plot that we looked at maybe a month or so ago. So this is the relationship between A by A star and Mach number, okay? So if this is AI by A star, then this is MI, okay? So this is AI by A star and A by A star and Mach number for different values of Mach number. And what we observed is that for a given value of A by A star, there are two values of the Mach number, one subsonic and one supersonic, right? And this MD, let's call this as the design, right? So this is, okay, this is AI, then this corresponds to AI by AT, where AT is the throat area, and which also happens to be the A star for the design condition, right? And then now, let me use another color. Let me use a green color. So this is the design Mach number. This is the current operating Mach number, MI. And if you plot the A by A star, then this guy is going to be AI by A star, okay? And MI is less than MD, okay? That is the condition that we are looking at. So MI is slower. The current speed is slower than the cruise speed. Then if AI by A star is less than AI by AT, then it's easy to infer that A star, that is the effective reference area for this operating Mach number MI, is greater than the design reference area, which is AT, which is the throat area under this. So which means the A star for this off design condition is greater than the A star for the corresponding design condition. This means for this nozzle, the M equals 1, or the sonic flow, which was supposed to have occurred at the throat, would now occur at an area of cross-section which is larger than the throat area. The problem is that your M equals 1 cannot occur anywhere, right? I mean, it needs to occur where you have some kind of an inflection in the area variation, right? So your dA by dx should be 0. That's the only place your M equals 1 can occur. Okay, that's the first one. The second one is the AT is the smallest area of cross section in the converging diverging nozzle. Now you just cannot have M equals 1 anywhere else. Okay, so what this means is, and in order to slow down the supersonic flow from M greater than 1 to M less than 1 into a very weak subsonic flow, you need to cross the region of M. Your flow should be M equals 1 somewhere in between, okay? Or you should have a shock. So if you were to do it isentropically, then your M should be equals 1 somewhere, right? Otherwise, you're going to have a shock. And what we are realizing is when A star is greater than AT, there is no location where M equals 1 can occur, which means the only mechanism for this fluid to slow down is through a shock. So what happens in reality is if you have MI less than MD but still supersonic coming in, and you have a nozzle that was designed for MD, then what you're going to end up with is a big red normal shock in front of this nozzle. And what are you going to have here, right? So, and then behind this normal shock, you're going to have a subsonic flow. So let's call this, so here M1 equals MI, and then here you're going to have M2, okay, which is less than 1, right? Which means if let A1 star, okay, so then A1 star is the reference area for this supersonic flow MI, then A2 star is going to be the corresponding reference area behind the shock, right? And what did we see? whenever you have a shock, the A star increases across the shock, right? So A star increases across the shock. Why? Because A2 star by A1, A1 star by A2 star is P naught 2 by P naught, A1 star by A2 star is P naught 2 by P naught 1, okay? And P naught 2 by P naught 1 is less than 1, which means A2 star is greater than A1 star. So the A star, or the reference area, always increases across the shock. And when the reference area increases across the shock, what this means is for the same mass flow rate behind the shock to pass through this nozzle, you need a bigger reference area or a bigger throat area to push the same fluid through the nozzle. But your A2 star, your A throat was already less than A1 star, which is obviously going to be less than A2 star, which means there is going to be excess fluid that is being that we are trying to push through this converging diverging nozzle. And if there is excess fluid and the flow is subsonic, then the only way the flow will respond is part of the flow is going to spill or bypass. So this is what is called as the spillage. So the flow is going to bypass this nozzle, and only the flow that this nozzle can handle corresponding to A2 star is going to pass through this nozzle, right? And now, which means the nozzle is going to be choked, and this nozzle throat area. Let me take that back. The nozzle is not going to be choked. The nozzle is going to have only so much flow that it can handle, and that corresponds to an area A2 star, right? So you have subsonic flow and you have a converging section, which means subsonic flow is going to accelerate, and then in the diverging section it can either accelerate or decelerate depending on what your back pressure is and whether the flow is already choked. Okay, so all kinds of things that will happen. So this is the typical response, and obviously the problem with this approach is you have a shock, and the shock is going to result in a loss of stagnation pressure. And so the approach to overcome this deficiency of the design is what is called as overspeeding maneuver. So if you're operating at a Mach number that is less than the design Mach number, then instead of just accelerating to the design Mach number, what you do is you accelerate beyond the design Mach number such that the shock that you're having gets swallowed into the nozzle, and then if you decelerate to the design Mach number, you will be able to remove the shock in its entirety, and I'm going to show you the mechanism of that. Okay, say MA is the operating speed, so this MA is less than MD and it's greater than 1, right? So it's off design but slower than the design condition, but it's still supersonic. So you're going to have a shock like this. So you're going to have this kind of normal shock in front of this nozzle, and then behind the shock you're going to have subsonic flow, and this subsonic flow is going to result in some extra fluid being spilled or bypassing the nozzle, and then only whatever the nozzle can handle is being pushed through. Okay, so now you have P naught, here you have P naught 2, P naught 1, your P naught 2 is smaller, so it's going to handle the rest of the fluid. Okay, so now if you increase, let me increase my MB. My MB is greater than MA, okay? And this is going to be equal to MD, okay, or my design Mach number. So now I'm increasing my Mach number to the design speed. When this happens, the shock doesn't go away. What happens is now my shock already exists, and this shock is going to get closer to this nozzle, and there's going to be less spillage. Okay, there's going to be less spillage because my A star is now closer to the A star, but the shock is not going to vanish all of a sudden, right? The shock still exists. So you're going to have, the shock is going to get pushed to the right. So the shock is getting pushed to the right and closer to the nozzle. And if I increase, So my MC is greater than MD. So if I increase my flight Mach number greater than my design Mach number, at that point the shock goes inside further and it gets into the nozzle geometry. So this is the point where we call as the nozzle, the shock being swallowed in the nozzle. Okay, so this is shock swallowed. Okay, and if I increase my Mach number to MD slightly greater, so this is a very small number, so if I slightly accelerate the flow, the shock that was here goes here. Okay, the shock goes there, and now my ME is the final stage where I decelerate. So this is, all of this is accelerate, right? So this is accelerate, this is accelerate, this is accelerate slightly, and this is decelerate to MD. When I decelerate, the shock that was here moves back into the throat region. And at the throat region, what is the Mach number? M equals 1, right? So M equals 1 is the Mach number at the throat, which means the shock that you have is the weakest shock, and which means you basically get rid of the shock and you get an isentropic flow. So this is isentropic flow, okay? So this is what is called as the overspeeding maneuver. So you can, when we meet next time, you can ask me the relevant questions regarding this material, but there's a lot of discussion about this in the textbook, okay? So now what you have is an isentropic flow here, okay? This is called as the overspeeding maneuver. So as the flight Mach number increases, the normal shock gets swallowed, and the flight Mach number is finally decreased to design conditions after this overspeeding maneuver, which means the shock moves to the throat with MT equals 1. So this is the weak shock limit, and the flow is isentropic with no loss of stagnation pressure. Okay. There's a note that is given in your textbook which I think is relevant. The case E in the above figure is the design condition, okay, which means it's purely isentropic. However, the operating at this design condition turns out to be unstable. What this means is any small change in Mach number is going to result in an off-design condition, and the shock that is at the throat right now and is an infinitesimally weak shock is going to all of a sudden come out and start become a very strong shock outside. Okay, so consequently, the recommended operation procedure is to have the shock. Okay, I'm sorry for the typo. So is to operate the flight with the shock slightly past the throat. That is, you operate, so if this is the nozzle, then you'll operate such that the shock is somewhere here, okay? Which means it is still a weak shock because here M is 1, right? So here M is 1, but here M is probably 1.1 or something like that. So it's still a weak shock. So there is going to be a little bit of momentum loss and stagnation pressure loss, but it's not as significant, and this is a more stable situation to operate in, okay? There's another method to swallow shocks, and this is a more common approach in the current day of active control technology. So the basic idea is, if you're operating in the off-design condition, then your A by A star, so this is the basic issue is this, right? So if you're operating the off-design condition, this is MI, then MI corresponds to AI by A star, this corresponds to AI by AT, and by design, AI by A star is less than AI by AT for isentropic flow, which means A star greater than AT, okay? So which means if you are operating in off-design condition, the converging diverging nozzle is not large enough to support this flow, and the only way the flow can respond, since the incoming flow is supersonic, is by having a shock in front of the nozzle, and which results in a subsonic flow behind the shock, and the subsonic flow also cannot pass through this nozzle, so part of the subsonic flow spills out, and only whatever the nozzle can support whatever flow rate the nozzle can support is passes through the nozzle. So now, instead of accelerating this flight beyond the design Mach number and coming and slowing it down to the design Mach number, which is called as overspeeding maneuver, the other thing that you can do is you can change throat area to absorb this flow. Okay. Okay. So you can change. This is the second approach. Okay. And the way to do that is the following. So let me put this M somewhere here. So this is my Mach number axis. So the way to do that is the following. So imagine this is the off design case, right? So this is my MI. So this is my MI. Okay, let me put it in green. So this is my MI. So MI is less than D. MD, that is it's slower than the design Mach number, and MI is still supersonic. Then I'm going to have A1 star, which is the reference area in front of the shock, and I'm going to have a shock, and behind the shock I'm going to have A2 star, right? So we obviously knew the following, so which implies that A1 star, so we're going to have this following gradation in the reference area. So my A2 star is the reference area behind the shock for isentropic flow. It's greater than A1 star greater than AT. Okay, so A2 star, so if you have an isentropic flow, if you take the isentropic flow behind the shock, then A2 star is the location at which Mach number will be 1. And obviously, since A2 star is greater than AT, the Mach number cannot be 1 for that flow. So what will happen is there'll be some of the flow that will be going through this nozzle, and some of the flow will be spilling out. So you're going to have what is called as spillage. So you're going to have spillage. Okay, and whatever can pass through this throat area AT is what is going to pass through. Okay, that's the amount of. So the approach is, so if you have this starting state, now this is A0. Okay, this is the throat area. This is A0 equals AT. Okay, this is AT. So AT is your starting throat area. Now you have some kind of a mechanism by which you can change the throat area. So now your AA is AT2. This is your new throat area. So you make the throat area equal to A2 star, which is the reference area for the subsonic flow, which means you're avoiding the spillage effect. So all the fluid that was supposed to have bypassed now passes through this. So there's no spillage, so all the guys are going to go inside, which means, and at this point, the shock that was outside now starts settling in at the mouth of this nozzle. And if I increase the area further, okay, now what is going to happen is the shock that was here is going to go here, right? But I'm going to increase the area slightly, so which means my flow, my delta A is going to be infinitesimally small. I'm just triggering the mechanism for the shock to move downstream. And now I change my throat area to match the design condition, which is smaller than my AA. So this is the reduction of throat area. This is a reduction of throat area. This is increase throat area. This is again increase throat area. Okay, so this is what I'm doing. So I'm increasing throat area once to swallow the shock, then I'm increasing it slightly more to push the shock downstream so as to make this shock system stable, and now I reduce the throat area to my design value, and basically my shock that was here, so this moves here to this location, and at that location m equals 1, which means what you have is an infinitesimally weak shock. Okay, so this is called as changing the area of the throat to swallow the shock. Okay, so there's an example problem in your textbook that I just want to quickly go over. I think I have. Let me just go over this solution quickly. It's an easy problem. Let me see what the deal is. Right, so what you have is a supersonic diffuser, so that is designed for m equals 1.7. So this is my MD. To what Mach number would the inlet have to be accelerated to swallow the shock during startup? So this is basically the overspeeding approach, right? Okay, this is the overspeeding approach. So you can draw the schematic. So this Mach number, obviously, this overspeeding is required only when you have operating in an off-design condition. So MA is less than MD, which is equal to 1.7, and obviously that's greater than 1. So this is somewhere, MA is somewhere between 1 to 1.7. That's the condition under which such a flow would happen. So obviously this is steady 1D flow, isentropic, etc. So we already know MD is 1.7, which means from this I can get AI by AT, which is the design nozzle shape, right, from Appendix B. Okay, so the basic idea is we need to find MB which corresponds to this image. Okay, so this is, let's look at this image. So the swallowing of the shock corresponds to this image C, right? So this is the swallowing of the shock, the first case when the shock is swallowed. So you want to find out what is the Mach number in front of the nozzle here. What is the Mach number of this flow, MB, such that this MB is obviously going to be greater than MD for this shock to be here, right? If the shock is here, then obviously you're going to have subsonic flow behind the shock, right? So so let's kind of solve this problem. So this is, let's do the final solution for this problem. So obviously, you know, in all your homeworks, it's important that you follow, write out the problem statement in a nice way and clearly specify what you're trying to do in your homework problem. Okay. So instead, the final solution step is the following. Okay. So now we know MD equals 1.7, which implies AI by AT is gonna be 1.3376, right? Now, what is going to happen is now you have a shock here, okay? Now, now after overspeeding, if it's really confusing to you, I suggest you kind of rewrite this as MC. So you have to find this MC, right? So now after overspeeding to MC, shock is at inlet plane. So, and which implies that behind the shock, so now you're going to have a 1 star here and a 2 star. And obviously if you have a shock in this nozzle and then this flow is choked, right? So your A2 star equals AT, correct? So A2 star equals AT, okay? So which implies that M2 at A1 by AI by AT equals A1 by AT is 1.3376 using Appendix B is M2 equals 0.5, okay? So this is the subsonic solution. Which implies that if M2 equals 0.5, what is M1 equals MC? What is MC, right? So this you can get from use appendix C, normal shock tables, to find the Mach number in front of the shock, and we get MC equals M1 equals 2.64. So you need to accelerate to a Mach number, okay? So the key, you need to accelerate to a Mach number of 2.64. The key realization here is when the shock is swallowed, you have a shock in the nozzle. And whenever you have a shock in the nozzle, the flow is choked, okay? And which means if you have a shock in the nozzle, then you have this isentropic flow region here, right? So there's only be one, this is isentropic flow, and for this isentropic flow there's only one A star, and that A star is going to be AT, and it's also going to be A2 star, okay? The A2 star is the same as AT. So if I know my AI, and the shock is occurring at AI, okay? So which means AI by AT is going to give me the subsonic flow solution at that location, which is 0.5. And the subsonic flow is accelerating. It will be M equals 1 here, and depending on the back pressure, PB, it will either accelerate or decelerate depending on which what value of back pressure you have. So this is the essential method to solve such problems, okay? And I think that brings us to the end of chapter 4. In the next class, we'll try to solve some example problems, and you can also ask me any questions about this material. Thank you.